Welcome to Space Dream's documentary. Tonight the universe drifts into focus as a quiet lattice of darkness and light. Filaments stretch like faint threads across immense voids. Galaxy clusters gather where those threads meet. This is the cosmic web shaped by gravity over deep time. If this kind of calm science journey is your favourite way to unwind, please like the video and subscribe to Space Dream's documentary. It helps the channel grow and brings more long-form space stories to the night. Now settle into the dark, the web is already forming. A silent lattice lies across the universe, and it is felt before it is seen. The cosmic web forms because dark matter shapes the slopes that ordinary matter later follows. In that region, space looks almost empty at first. A thin haze of matter spreads in all directions. Then faint differences appear. Some patches hold slightly more mass. Some hold slightly less. Gravity turns those small differences into paths. The paths do not look like lines drawn on a surface. They look like gentle ridges in an invisible landscape. A ridge does not need sharp edges to guide motion. A shallow tilt is enough. A drift begins toward the lower places. A drift begins away from the higher places. At this distance, the first hint of structure is not a bright object. It is a pattern of preference. Matter prefers certain routes. It avoids others. The web begins as a bias that grows calmer and stronger with time. A single filament can stretch for hundreds of millions of light years like a weather band that spans an entire ocean. That scale sounds extreme, yet the guiding idea stays simple. Where the gravitational landscape has long ridges, matter gathers into long strands. Where ridges intersect, matter gathers into knots. Where the landscape forms broad basins, matter drains away and leaves wide voids. The first unlock arrives quietly. A filament is not a rope. It is a region where the density is slightly higher than around it. That slight difference is enough to steer flow for billions of years. In a slow scene, a dark volume holds a faint mist. The mist is uneven by a whisper. Over long time, the brighter mist becomes threads. The threads curve and fork. They meet at thicker junctions that glow more strongly. The space between threads stays thin and dim. Boundaries appear without sharp walls. A gradient forms instead. The density rises toward the thread center. It falls away toward the void. The web is geometry made from gradients. The physical detail is not a hard surface. It is a soft thickness that has a center line. Around that line, matter moves as if along a shallow trough. In that region, motion does not look fast. It looks patient. The change is not dramatic in a moment. It is dramatic across ages. A second unlock settles in. Dark matter does not need collisions to build this scaffold. It behaves as mostly collisionless mass. That means it passes through itself without sticking. One sentence defines it. Collisionless means particles rarely collide and mostly feel gravity. Two sentences return to plain imagery. Like dry silt in a broad current, it can stream and overlap without clumping into one solid piece. Like fine dust in still air, it can form thicker streaks where flows converge. One sentence explains why it matters. A web built from collisionless flow can form early and guide everything later. A new visual anchor appears with slow clarity. A filament is seen edge-on. It is not a line. It is a thick ribbon with a denser spine. The spine is wrapped by a fainter sheath. The sheath fades outward. Tiny clumps ride inside the ribbon. They are like darker grains inside a pale strand. The strand bends around a low, massive knot. The knot is not a point. It has a rounded core and a wider halo. Around it, matter orbits and mixes. The geometry is layered. A core sits inside a broader envelope. Outside, the filament feeds the envelope like a long inlet. The scale shifts gently. In a small cloud, a slope guides a droplet across a leaf. In the cosmic web, a slope guides entire galaxies across intergalactic space. The principle is the same, only the patience changes. The next unlock arrives in plain language. Ordinary matter follows the scaffold because it cannot ignore gravity. Gas drifts into the same troughs as dark matter. It does not arrive in the same way. Gas can cool and compress. It can make sharper edges than dark matter does. It can form sheets and shocks where flows meet. Even then, the first map is still the dark one. In that region, light behaves as a messenger that reacts to the scaffold. It brightens where gas heats. It dims where gas thins. Yet brightness is not the same as mass. A bright patch can be small. A dim patch can hold a wide, heavy halo. That mismatch is a calm source of confusion. It is also a guide to deeper understanding. A limit of intuition appears softly here. The web cannot be seen directly where it is truly dark. Any outline must be inferred from effects on light and on motion. A signal would show bending and stretching as it passes near dense knots. A signal would also blur together structures that sit along the same line of sight. Depth can collapse into a flat projection. Two filaments can overlap and look like one. A thin sheet can hide behind a thicker strand. Resolution sets another limit. If the sampling is coarse, a filament looks like a mild smudge. If the sampling is finer, the filament reveals substructure and branching. The web is real, yet any picture of it depends on how the picture is formed. The next visual anchor slows the pace again. A wide void appears as a dark basin. Its edges are not walls, they are pale curtains. The curtains are made from thin sheets where matter piles up. The void interior is not empty. It holds faint wisps and sparse islands. The contrast is gentle. The difference is in thickness, not in presence versus absence. Along the boundary, the density climbs like a shoreline that rises from deep water to shallow sand. The everyday analogy settles in. Like a delta where slow currents lay down sediment in branching channels, matter lays down structure along paths that carry flow. The channels are not carved by tools, they are carved by gravity. The delta analogy unlocks a detail. Branching is not decoration. Branching is the natural result of many shallow slopes competing. A flow chooses the easiest descent. The easiest descent changes when another ridge grows nearby. Over time, some channels deepen, others fade. A second scale shift arrives without strain. A grain of silt settles in seconds. A cosmic filament thickens over billions of years. The same quiet tendency plays out across different clocks. Another payoff appears as a small answer. The web does not require a central organizer. It arises from local slopes repeated everywhere. Each region follows the gradient nearby. The global pattern emerges as those local choices join. The final visual anchor of the section returns to a single junction. Several dim strands approach a knot from different directions. The strands narrow as they near the knot. The knot shows a rounded center and a wide halo. Around the halo, faint arcs of matter curve like ripples around a deep stone in a pond. The arcs are not waves in water. They are layers in phase space where many streams overlap. The physical detail is subtle but firm. The overlap creates a sharper change in density at certain radii. The edge is not a shell of rock. It is a boundary in motion. It marks where infall turns into orbit. It marks where fresh streams meet older layers. The scene holds stillness and slow movement at once. The web is a structure of paths, not a structure of rigid beams. It is a scaffold made from gravity and time. The transition stays gentle. The next section moves backward toward earlier time where the first unevenness begins as a nearly smooth field. The same quiet logic continues but with smaller contrasts and softer beginnings. A nearly even beginning holds a faint unevenness that never fully disappears. The cosmic web grows because tiny density differences deepen under gravity, while expansion stretches everything outward. In that early era, space carries a soft background glow. It looks smooth at first glance. Then a fine mottling becomes noticeable. Brighter patches sit beside slightly dimmer ones. The contrast is extremely small. It is about 1 part in 100,000, like a long tabletop, that varies by the height of a single grain of sand. That smallness is the first quiet key. A difference does not need to be large to matter. It only needs time. The first payoff arrives gently. A tiny surplus of mass pulls a little more mass toward it. That added mass makes the pull slightly stronger. The process repeats without hurry. It resembles a slow fold forming in stretched fabric. A sheet that begins almost flat can develop shallow creases. The creases deepen where the material gathers. In that region, the fabric is not dragged by hands. It responds to tension and to its own weight. In the cosmos, gravity plays the role of tension. The fold is a filament in its earliest form. A visual anchor settles into focus. A broad, dim sphere of ancient light surrounds the scene like a distant shell. Across that shell, faint speckles form a pattern of warmer and cooler tones. The speckles are not objects. They are hints of density. They mark places where matter is slightly more crowded. They also mark places where matter is slightly thinner. Between them, the glow stays calm and uniform. The mottling is gentle. It does not look like storms. It looks like fine grain in polished stone. Another payoff arrives without raising the voice. Those tiny differences already contain the map of later structure. The web is not drawn later from nothing. Its blueprint exists as a weak pattern that grows stronger. One term can be used and kept simple. A density fluctuation means a small difference in mass from place to place. Two sentences return to plain imagery. Like a blanket with slightly thicker patches, it sags a little more where it is heavier. Like a quiet drift of powder, it settles more where the slope is slightly deeper. One sentence explains why it matters. Those small differences decide where filaments and clusters later appear. A second visual anchor moves closer. In a dark volume beneath the glowing shell, invisible mass begins to gather. The gathering has no sharp edge. It has a gradient. The center grows denser. The outskirts remain thin. The boundary is not a wall. It is a gradual change in thickness. Streams begin as broad flows. They narrow as they approach the denser center. The narrowing is slow. It is guided by a shallow tilt in the gravitational landscape. The scale shift arrives quietly. A subatomic imbalance can seed a macroscopic pattern. Then hundreds of millions of years pass. The same imbalance becomes a filament longer than any familiar distance. Time turns whispers into contours. Another payoff fits into a single clear answer. Expansion does not erase structure. It competes with gravity. When expansion dominates, growth is slow. When gravity wins locally, growth accelerates. The same region can be stretched overall and still collapse in parts. That balance shapes the web into strands and voids. The fabric analogy returns with a new detail. Stretching can make folds longer and thinner. It can also leave wide flats between folds. Those flats become the first voids. Another visual anchor appears at the right pace. A forming filament looks like a pale band in darkness. Its spine is slightly thicker than its edges. Along the spine, small knots appear as faint beads. The beads are not placed evenly. Some sit close together, some sit far apart. The spacing reflects the original pattern of speckles. The filament also shows subtle tapering. It thickens toward a junction. It thins toward a branch. The physical detail is a quiet geometry of narrowing corridors. The corridors guide flow without needing borders. A limit of observation enters softly. The early pattern is not measured by touching matter itself. It is inferred from the ancient light that carries the imprint of those speckles. That imprint is indirect. It is also blurred by thickness along the line of sight. Many layers overlap into one view. Small features can be washed out. Resolution sets a hard ceiling. If the pattern is sampled too coarsely, different scales blend together. A single patch can hide several smaller variations. The map becomes smoother than reality. Models also add limits. Growth depends on what the unseen mass is like. If its properties are assumed wrongly, the predicted web shifts in subtle ways. The web can be consistent with many details that remain uncertain. That uncertainty stays calm. It does not remove the main picture. It only softens the finest lines. Another payoff arrives as a quiet correction. The first structures grow in the dark component. Ordinary gas does not lead the process. Gas feels pressure. It resists compression. It can be heated by even mild squeezing. The unseen mass does not feel that pressure in the same way. It can pile up earlier. It can make deeper troughs. Then gas slides into those troughs later. That sequence matters because it sets the timing. Filaments appear in the mass field before they shine strongly. Another visual anchor brings the scene forward in time. The ancient speckled shell remains now farther in memory than in view. The dark volume shows clearer pathways. A broad sheet of matter becomes slightly curved. The curve steepens toward a ridge. The ridge thickens into a strand. Along the strand, faint clumps begin to orbit within a wider halo. The halo has a soft outer edge where infell turns into wandering motion. The edge is not fixed. It shifts outward with time. The scale shift repeats in a gentler tone. The change from smoothness to structure is slow on any short clock. It is decisive on the clock of billions of years. The fabric of space remains calm, yet its contents gain shape. The section closes with a soft step ahead. As the dark scaffold deepens, the luminous matter begins to trace its corridors more clearly. The next section moves into those corridors and follows how strands and junctions take on their familiar form. A filament becomes visible not as a line, but as a place where flow chooses a corridor. Ordinary matter traces dark matter because gravity makes the same low paths inevitable. At this distance, the corridor is wide. It has no walls. It has a center where density is higher. It has edges where density fades. The fade is a gradient. The gradient is the physical signature. It behaves like a shallow valley in a landscape made of mass. A stream does not need to see the valley. It only needs to feel the tilt. Gas drifts along the tilt. Dark matter streams along the tilt. The early answer settles in. Filaments are highways made from slopes, not tubes made from material. The main number arrives calmly. A typical filament can be about a few million light years thick, like a fog bank wider than the distance across an entire galaxy. That thickness matters because it sets the channel size. A broader channel gathers more flow. A narrower channel funnels it faster. The first visual anchor unfolds in a slow scene. A long dim strand stretches across darkness. It is not uniform. It thickens toward a junction. It narrows toward a branch. Along its spine, faint clumps appear like beads embedded in a translucent ribbon. Around the spine, a softer sheath surrounds it. The sheath looks like a pale halo that fades outward. The boundary is not sharp. It is a gentle edge where the haze becomes harder to distinguish from the void. Another payoff arrives as a quiet mechanism. Dark matter streams can overlap. Overlap raises density without needing collision. Raised density deepens the valley. A deeper valley draws in more flow. Gas arrives later and behaves differently. Gas can cool. It can compress. It can form denser knots inside the same valley. It also resists sudden squeezing because pressure pushes back. That pushback creates shape. A filament in gas can show a flatter core. It can show a layered profile. The inner region cools and condenses. The outer region stays warmer and diffuse. A second visual anchor appears at the right pace. Along one segment, a faint sheet lies beside the filament. The sheet is like a thin veil. It curves and folds toward the strand. Where the sheet meets the strand, a subtle ridge forms. The ridge is a place where flow converges. The physical detail is a crease. The crease is not a tear. It is a narrow region where density climbs steeply compared with its surroundings. Another payoff resolves a small puzzle. Branching is not accidental. It forms because many shallow valleys compete. When two valleys run near each other, the flow divides. One stream chooses one tilt. Another stream chooses the other. Over time, one branch may deepen. Another may fade. The web is not fixed like a net. It evolves like drainage patterns across a wide plain. The everyday analogy arrives as the main comparison. Like threads in slow-moving syrup filaments form where flow keeps choosing the same lanes. Syrup does not need channels carved into a bowl. It forms its own thicker strands as it stretches and gathers. The analogy unlocks a detail. The strands in syrup appear where stretching and convergence overlap. In the cosmic web, stretching from expansion and convergence from gravity overlap too. The same combination builds long coherence and gentle curvature. The scale shift slides in softly. A droplet of syrup thickens a strand in seconds. A filament thickens in the cosmos over billions of years. The shape is familiar. The clock is not. Another visual anchor returns to motion. Inside the filament, matter does not move straight. It streams inward and also along the axis. The axis is the long direction of the strand. The inward drift feeds the spine. The along-axis drift feeds the junctions. Near a junction, the spine becomes denser. The sheath becomes brighter in traces. The junction sits like a rounded knot with a broad skirt. The skirt shows subtle arcs. The arcs come from overlapping streams that turn from infall into orbit. The physical detail is a ring-like layering in density. It is not a perfect ring. It is a gentle set of curved bands. Another payoff arrives as a clear takeaway. Filaments do not only connect clusters. Filaments build them. They deliver mass steadily. They also deliver it from many directions. That multi-direction feeding makes junctions grow faster than isolated regions. The limit of observation enters with soft precision. The dark scaffold cannot be seen directly. The filament is inferred from luminous matter, which can be biased. Gas can cool in some places and heat in others. That changes brightness without changing total mass much. Projection adds another limit. A filament aligned with the line of sight can look denser than it is. A filament crossing the line of sight can be diluted. Resolution sets a third limit. If the sampling is coarse, branching disappears. The web looks smoother and simpler than reality. Models fill gaps, yet different model choices can shift where filaments appear strongest. The main picture remains stable. The fine texture stays uncertain. A final visual anchor slows the scene before transition. A wide void sits beside the filament like a quiet bay. The bay is not empty. It holds faint wisps that drift away from the filament edge. Along that edge, the gradient steepens. The haze brightens gently. The filament looks like a shoreline made of mass. The shoreline does not stop anything. It guides motion. The section closes with a soft step forward. As corridors feed junctions, intersections begin to heat and layer. The next section moves into the geometry of those corridors and how strands fork and merge without sharp boundaries. A filament does not end at a junction, it changes shape and becomes a meeting place for many slopes. The cosmic web gains its familiar pattern, because strands fork, merge and thicken where gravitational basins overlap. In that region, several corridors approach one another from different directions. Each corridor has a soft center line. Each has an outer sheath where density fades. Where two corridors draw near their gradients overlap. The overlap creates a broader valley. Flow becomes less one-dimensional. It begins to spread into a sheet before it narrows again. The first payoff arrives as a simple clarification. Forks are not splits caused by impact. Forks appear where the landscape offers two equally gentle descents. Matter follows the least resistant tilt, and the least resistant tilt can have more than one branch. A slow, visual anchor opens. A pale wall of matter stretches like a thin curtain. It is wide and faint. Its edge is slightly brighter where it folds. Along that fold, a filament runs like a seam. The seam is thicker than the wall. The wall is thinner than the filament. The boundary between them is gradual. It looks like a dim gradient sliding from sheet to strand. The physical detail is the layering. A thin sheet feeds a thicker seam. The seam feeds a rounded knot. The knot sits where several seams converge. The knot has a denser core and a broader halo. The halo fades outward into surrounding filaments. Another payoff arrives as a quiet mechanism. When basins overlap, motion gains a new direction. Matter can drift inward toward the knot. It can also drift along the seams. It can also drift within the sheet toward the seam. 3 directions exist, yet the motion remains slow. The web becomes a network because the same mass can be guided by more than one gradient at once. A new term can appear and stay short. A caustic is a thin layer where many streams pile up. 2 sentences return to plain imagery. Like a wrinkle in a thin cloth where several folds meet, it makes a sharper ridge than the cloth around it. Like foam edges where bubbles press together, it forms brighter lines between wider cells. 1 sentence explains why it matters. Caustic-like layers mark where infall turns into orbit and where density rises quickly. The main number arrives calmly. A junction can grow for about 1 billion years like a slow river confluence that deepens its basin through many seasons. That duration matters because it allows repeated feeding. A junction does not form once and stop. It keeps gathering. It keeps adjusting as new seams arrive. The second visual anchor shifts closer to the knot. The knot's outskirts show subtle arcs. The arcs look like faint bands of slightly higher density. They are not perfect rings. They are partial curves that wrap around the core. They mark where streams have turned. They also mark where new streams cross older layers. The physical detail is a boundary in motion. The boundary is not solid. It is a change in direction. A stream enters from a filament. It bends and begins to orbit. The bend produces a layered edge. Another payoff arrives as a clear answer to a quiet question. The web looks like lines and nodes because gradients sharpen at intersections. A single filament has 1 main direction. A junction has many. The extra directions make it easier for matter to linger. Lingering raises density. Raised density deepens the basin. Deepening attracts even more flow. The process is steady. The tone remains calm. The everyday analogy becomes the main comparison for this section. Like braided strands in a slow-moving tide line, several filaments can weave together and leave a thicker ridge at their meeting point. The tide line is not a wall. It is a place where repeated gentle passes deposit more material. The analogy unlocks a physical detail. The ridge is built from layers. Each pass adds a thin sheet. Over time, the ridge becomes a seam. In the cosmic web, each inflow adds a layer in phase space. Layers overlap and create sharper bands. The scale shift arrives softly. A shoreline ridge can form over days. A junction ridge forms over billions of years. The same idea repeats across clocks. Another visual anchor appears at the right pace. A wide void sits beside the wall. Its interior is darker and thinner. Along the void edge, the wall brightens. The wall folds toward the seam. The seam narrows toward the knot. The knot thickens and rounds. The geometry resembles a slow funnel made from haze. The haze has no sharp edge, yet it has a direction. Matter drifts as if guided by shallow grooves in air. Another payoff arrives as a small unlock. Sheets help explain why the web is not only filaments. 2 filaments can be part of one larger plane. That plane can be hard to notice because it is thin. It can also be missed if viewed edge-on. A limit of observation enters with gentle precision. The 3-dimensional web is often reduced to a 2-dimensional picture. Projection can hide sheets by stacking them with other structures. A sheet viewed face-on can appear as a mild brightness change. A sheet viewed edge-on can masquerade as a filament. Resolution creates another limit. If sampling is sparse, seams look straighter than they are. Branches disappear. Models can infer missing structure, yet different assumptions change where walls should be strongest. The main pattern remains stable. The fine weaving stays uncertain. Another visual anchor slows the scene before the closing transition. A junction breathes with slow infall. Filaments feed it like long, dim ribbons. The ribbons taper near the core. The core remains rounded. The outer halo stays diffuse. A faint boundary marks where fresh infall joins older orbits. The boundary looks like a soft rim. It is a place where density changes faster than elsewhere. The section closes with a gentle step ahead. As junctions grow, gas heats and layering becomes more distinct in the brightest knots. The next section moves into those knots and follows how voids and clusters become the quiet extremes of the same web. A void looks like absence, yet it carries a shape that gravity carefully maintains. Voids form because matter drains toward filaments and nodes, leaving wide basins with thin interiors and defined edges. In that region, darkness is not uniform. It has a faint texture. A few wisps drift like diluted smoke. The center holds less material than the rim. The rim holds more material than the center. The difference is a gradient. That gradient is the physical detail that matters. It is not a cliff. It is a slow rise in density toward the boundary. The first payoff arrives as a simple correction. A void is not a hole cut out of space. It is a place where the web has pulled mass away more efficiently than average. The draining begins early. It continues for a long time. The main number appears softly. A large void can span about 100 million light-years like a single bubble, large enough to contain many thousands of galaxies with room to spare. That scale sounds vast, yet the mechanism stays gentle. Matter slides down shallow slopes toward denser ridges. What remains is a basin. The basin keeps expanding as the surrounding walls thicken. A slow visual anchor settles in. A wide, dim cavity sits between two pale walls. The walls are not flat. They curve and bow inward in places. Along the walls, thin sheets form like faint curtains. Where curtains overlap, brighter seams appear. Those seams are filaments. The void boundary looks like a soft shoreline. It is brighter than the interior. It is also slightly thicker. The interior looks thinner and smoother. The rim shows faint rippling layers where flows have passed. Another payoff arrives as a clear answer. Voids grow not by sucking matter inward, but by pushing it outward in relative terms. Expansion stretches the interior faster because there is less gravity resisting it. The rim resists expansion more because it is denser. Over time, the contrast increases. The interior becomes emptier. The rim becomes more pronounced. The everyday analogy becomes the main comparison. Like a drying sponge that pulls moisture into its thicker strands, a void opens as material concentrates into the surrounding network. The sponge does not remove material from existence. It redistributes it into ribs and edges. The analogy unlocks a detail. The rib becomes stiffer where more material gathers. In the cosmic web, the boundary becomes sharper where more mass accumulates. The sharpness is still a gradient. It is a steeper gradient than before. A new term can appear in a quiet way. A density contrast is a ratio of thick to thin regions. Two sentences return to plain imagery. Like a lake surface that lowers while the shoreline stays high, the difference becomes easier to notice. Like fog that clears in the middle but remains at the edges, the boundary stands out. One sentence explains why it matters. Density contrast makes voids reliable markers of how structure has grown. Another visual anchor arrives at the right pace. Inside the void, a faint filament remnant stretches like a pale thread that never fully disappears. It is thinner than the main network. It fades into the interior. Small clumps sit along it like scattered grains. They are isolated. They do not connect strongly to the walls. The physical detail is the thinness and the fading. The void interior is not blank. It is underfed. That underfeeding changes how quickly new knots can form. Another payoff follows as a small unlock. The void interior becomes a quiet laboratory for the rules of growth. With less mass nearby, gravity has fewer opportunities to amplify small differences. Growth slows, isolation increases. The web becomes more obvious by contrast. The scale shift arrives softly. In a small container of fluid, a bubble rises in seconds. In the cosmos, a void rises into prominence over billions of years. The similarity is not motion upward. It is the appearance of a coherent cavity. Time does the work. Another visual anchor moves along the rim. The boundary shows a slight flattening in places. It shows thicker bulges in others. Those bulges align with nearby filaments. Where two filaments run close, the rim is thicker. Where filaments are farther, the rim is thinner. The rim also shows a subtle layered edge. A faint band sits outside a brighter band. The bands mark where matter has piled up in stages. The physical detail is layering at the boundary. It is a record of slow outward flow from the interior. Another payoff arrives as a clear explanation. Voids are not only shaped by what leaves, they are shaped by what surrounds them. Nearby nodes pull harder in some directions. That makes the void slightly elongated. The elongation is gentle. It is like an oval rather than a perfect circle. The web is anisotropic. It has preferred directions. That preference comes from the surrounding filaments and junctions. A limit of observation enters with calm precision. Voids are defined by what is not there. That makes measurement sensitive to traces. If only bright galaxies are used, the interior can look emptier than it is. If fainter traces are included, subtle structure appears. Projection adds another limit. A deep void can overlap with a shallow overdensity along the same line of sight. The cavity can be partially filled in appearance. Resolution sets a further limit. Small voids inside larger voids can be missed. The map becomes simpler than reality. Models can define boundaries in different ways. Different definitions shift the measured size. The existence of basins remains clear. The exact edges can vary. The final visual anchor steadies the tone. A vast cavity rests between pale walls like a quiet valley between distant ridges. The walls carry seams that lead toward a brighter knot far away. The knot is not approached yet. The void remains the focus. Its interior stays dim and smooth. Its boundary stays slightly brighter and layered. The section closes with a soft step forward. As matter gathers at the rims, junctions become hotter and denser. The next section moves into those junctions where many corridors meet and where clusters begin to form. A cluster begins as a junction that grows heavy enough to hold heat and motion in place. Galaxy clusters form where many filaments deliver mass until a deep basin builds a hot layered atmosphere. In that region, the web does not look delicate anymore. Several strands thicken as they approach one knot. The knot has a rounded core. It has a wide halo around it. The halo fades into the incoming corridors. The physical detail is the edge where infall changes character. A faint rim appears at a certain radius. Inside the rim, paths curve and loop. Outside the rim, paths stream inward more directly. The first payoff arrives as a clear answer. A cluster is not just many galaxies near each other. It is a gravitational basin that holds gas, dark matter, and orbits in one connected structure. The basin is deep enough to heat gas by compression and mixing. The heat makes the cluster glow in ways that reveal its shape. A slow visual anchor settles in. A bright knot sits at the meeting of three dim ribbons. Around the knot, a soft haze fills a wide sphere. The haze is thicker near the centre. It becomes thinner outward. The centre is smoother. The outskirts show faint ripples. The ripples trace layers where flows have joined. The boundary is not sharp. It is a gradient. Density and temperature change steadily with radius. Another payoff arrives as a quiet mechanism. Gas falls inward and speeds up. It cannot keep that speed forever. It meets other inflows. It is slowed and stirred. Energy spreads into heat. That heat puffs the gas into a broader atmosphere. The atmosphere stays bound because gravity is strong. The main number arrives calmly. A large cluster can contain about 1,000 galaxies, like a city-sized crowd gathered within one vast arena of space. The comparison is not about people. It is about count and density. Many separate systems share one basin. The count matters because it signals the basin's depth and reach. The deeper the basin, the more streams it can hold. Another visual anchor arrives on pace. The cluster outskirts show a faint arc like a soft crescent in the haze. The arc marks a region where inflow piles up briefly. It is not a wall, it is a compression layer. The layer curves around the cluster. It is thicker on one side where a filament feeds more strongly. It is thinner on the opposite side. The physical detail is a symmetry. The cluster is not perfectly round. Feeding makes it lopsided. Another payoff resolves a small question. The cluster keeps growing because the web keeps delivering. Filaments act like steady supply lines. They bring dark matter that deepens the basin. They bring gas that adds to the atmosphere. They bring smaller halos that merge into the whole. Growth is not smooth. It happens in quiet steps. Each step leaves a trace as layering and rippling in the outskirts. The everyday analogy becomes the main comparison. Like a slow whirlpool in thick cream, a cluster gathers inflow and turns it into a rounded layered pool. The cream does not fall straight to the centre. It spirals and mixes. It forms a thicker core and a smoother surface. The analogy unlocks a detail. Mixing spreads energy without needing a single violent event. In a cluster, mixing spreads heat through gentle turbulence. The scale shift arrives softly. A swirl in a bowl forms in seconds. A cluster settles over billions of years. The shape can look similar. The clock is radically different. Another visual anchor holds attention. Near the centre, the gas looks denser and smoother. Farther out, faint bands appear like contour lines. The bands are where many streams overlap in motion space. They can create sharper changes in density than expected from a simple gradient. The physical detail is a layered edge. The edge is a record of past infall. It marks where fresh material joins older orbits. Another payoff arrives with a calm clarity. The cluster is a memory of its feeding history. Strong feeding along one filament leaves a plume-like extension. Past mergers leave elongated halos. The present structure carries those imprints as gentle distortions. A perfectly round cluster is rare because the web is directional. The web supplies mass along preferred corridors. The corridors leave their signature in shape. The limit of observation enters softly and precisely. The cluster mass cannot be weighed by brightness alone. Bright regions can be hot gas. Dim regions can still hold large dark halos. Any mass map relies on indirect methods. Light bending can indicate mass distribution, yet the signal can be weak at the outskirts. Projection adds uncertainty. Foreground and background structures can overlap and mimic extra mass. Resolution sets another limit. Fine layering can blur into a smooth profile. Small subclusters can hide inside the main halo. Models can separate these effects, yet different assumptions shift the inferred total. The broad picture remains stable. Clusters are deep basins at web junctions. The fine details can vary with method. Another visual anchor slows the scene near the end. A filament approaches the cluster like a dim ribbon. As it nears, the ribbon thickens. Its sheath brightens in traces. The ribbon fades into the cluster atmosphere rather than stopping. The transition looks like a river entering a sea and losing its boundary. The physical detail is that dissolving edge. The edge shows a gradual change from directed flow to orbiting motion. Another payoff arrives as a quiet conclusion. The web does not end at clusters. Clusters are the web's most concentrated knots. They are built from the same gradients that shape voids and filaments. The same rules persist, only amplified. The section closes with a gentle step forward. Inside these basins, heat and motion create boundaries that look like fronts and rims. The next section moves into how orbits settle, and how clusters develop layered structure without losing calm. A cluster can look still from afar, yet its interior is a slow choreography of paths and layers. Clusters settle because orbits mix and spread energy, until a stable profile emerges without becoming perfectly smooth. In that region, motion is not random. It has structure. Infall arrives along filaments. Some material plunges inward. Some swings past the centre and returns. Some begins a looping path and stays bound. The first payoff arrives early and quietly. Settling does not mean stopping. Settling means the overall shape becomes steady even while individual orbits continue. The basin holds a persistent gradient. Density is highest at the centre. It falls outward. Temperature in the gas tends to rise toward the inner regions, then soften farther out. The physical detail is the layered boundary where new infall joins older orbits. It appears as a faint rim. Inside that rim, motion is more mixed. Outside it, motion is more directed. The main number arrives calmly. A typical orbit time in a cluster can be about 1 billion years, like a slow, seasonal cycle, repeated 1,000 times before a familiar landscape appears. The comparison is about patience and repetition. Many orbits are needed for mixing to matter. One pass does little. Many passes spread energy and blur sharp features. A slow visual anchor opens. A wide halo of thin haze surrounds a denser core. The haze shows subtle bands. The bands are gentle arcs that curve around the centre. They are not perfect rings. They are incomplete layers where many streams overlap. Each layer is slightly brighter than the space between. The edges of the bands are soft. They fade rather than cut. The physical detail is a sequence of faint shells and rims. Some lie close to the core, some lie farther out. The shells are the imprint of past infall stretched and softened by time. Another payoff arrives as a clear mechanism. When many orbits cross in the same region, density increases without needing collisions. Streams overlap in space. They also overlap in velocity. That overlap creates a smoother profile even if the underlying motion stays complex. One term can be used and kept short. Phase mixing means orbits spread out and fill available paths. 2 sentences return to plain imagery. Like dye stirred into a bowl of clear water, the colour spreads without needing a single strong splash. Like leaves drifting in a broad eddy, the distribution becomes even while each leaf keeps moving. One sentence explains why it matters. Phase mixing turns sharp infall features into gentle layers that define the cluster's profile. A second visual anchor arrives at the right pace. A filament enters the cluster outskirts like a dim ribbon. Near the boundary, the ribbon frays. Its spine becomes less distinct. The sheath blends into the cluster haze. At the blending zone, a thin arc brightens. The arc curves across one side of the halo. It is thicker near the filament entry. It is thinner away from it. The physical detail is asymmetry in a boundary layer. It shows that settling is ongoing. The cluster remains fed. Another payoff resolves a small question. The cluster can be stable without being spherical. Stability means forces balance on average. It does not require perfect symmetry. Continued feeding keeps small distortions alive. Merging substructures can leave elongated halos. Over time, these distortions soften. They do not always vanish. The everyday analogy becomes the main comparison for this section. Like a slow stack of thin cloth layers settling under its own weight, a cluster develops a smooth profile from many overlapping passes. The cloth does not become a single solid slab. It keeps its layers. Pressure and weight spread the layers. Gaps fill in. Edges soften. The analogy unlocks a detail. Each new layer changes the slope for the next layer. In the cluster, each new infall stream reshapes the potential slightly. That reshaping changes how later orbits turn and mix. The scale shift arrives softly. A cloth fold settles in minutes. A cluster fold settles in billions of years. The same calm tendency works across different clocks. Another visual anchor brings attention to the core. The core looks denser and smoother. It shows fewer sharp rims. The gas there can be thicker. It can be more uniform. Farther out, the gas becomes thinner. Ripples and arcs become easier to see. The transition from core to outskirts is gradual. It is a continuous gradient. The physical detail is the change in texture with radius. Smoothness inside, layering outside. Another payoff arrives as a quiet clarity. The outskirts keep memory longer than the core. The core mixes faster because paths cross more frequently. The outskirts mix more slowly because orbits are wider. That means the cluster's history is often written at its edges as faint rims and arcs. The limit of observation enters with gentle precision. Those rims are faint. They can be blurred by projection since unrelated structures overlap along the line of sight. They can also be blurred by resolution since thin layers can fall below detection thresholds. The inferred smoothness can be partly an artifact of measurement. Models help interpret the profile. yet different model choices can shift the inferred amount of mixing. Another limit appears in tracers. Gas brightness depends on density squared in many regimes. That can overemphasize dense regions and hide thin shells. A mass map from light bending can reveal shells, yet the signal can be noisy. The shells exist, but they can be easy to miss. Another visual anchor slows the final movement. A thin arc drifts outward like a fading wake. Behind it, the halo looks calmer. Ahead of it, fresh infall approaches along a filament. The arc is not a wave on a surface. It is a boundary between older mixed material and newer arriving streams. The boundary is curved. It is soft. It marks where motion changes character. The final payoff arrives as a gentle landing. A cluster is not a finished object. It is a stable pattern in continual slow change. Stability comes from repeated mixing and layered accretion. The section closes with a soft step forward. Where inflows meet more sharply, boundaries can become warmer and more distinct. The next section moves into those meeting zones and follows how shocks and fronts shape the cluster atmosphere. A quiet boundary can travel through a cluster and leave a lasting edge in the haze. Shocks and fronts form because converging flows compress hot gas into thin layers with sharper gradients than the surrounding atmosphere. In that region, the cluster gas is already warm and diffuse. It fills a broad volume. Incoming streams arrive along filaments. Smaller halos drift inward. Their gas meets the cluster gas. Motion cannot pass through without consequence. The first payoff arrives early. A shock is not an explosion. It is a moving surface where gas properties change quickly across a thin zone. One term can be used and kept short. A shock front is a thin layer of compressed and heated gas. 2 sentences return to plain imagery. Like a slow wave moving through tall grass, it changes the grass direction in a narrow band. Like a squeeze travelling along a soft mattress, it makes one region denser before it relaxes. One sentence explains why it matters. Shocks turn bulk motion into heat and help set the cluster's temperature structure. A slow visual anchor opens. A broad halo of faint glow surrounds the cluster. Across one side, a curved edge appears. It looks like a pale arc. Inside the arc, the haze is slightly brighter. Outside the arc, the haze is thinner and dimmer. The boundary is crisp compared with the rest of the cluster. It is still not a hard line. It is a steep gradient. The physical detail is the narrowness of that gradient. The arc is like a contour cut into mist. Another payoff arrives as a calm explanation. The arc marks where an incoming stream is slowed. Compression raises density. Raised density increases emissive brightness in many regimes. The edge becomes visible because a small change is concentrated into a thin layer. That concentration is the key. Without it, the change would be spread and hard to notice. The main number arrives gently. The thickness of a shock layer can be tiny compared with the cluster, like a sheet of paper compared with a room. The comparison is about relative thinness, not exact size. The layer is narrow, the cluster is enormous. A thin layer can still shape what is seen because it gathers contrast into one place. Another visual anchor appears at the right pace. A smaller halo approaches the cluster core. Ahead of it, the gas shows a faint bow shape. The bow is brighter along its leading edge. Behind it, a dim wake trails like a softened tail. The bow is not symmetric. It is thicker on the side facing denser gas. It is thinner on the far side. The physical detail is the bow curvature and the wake gradient. Another payoff arrives as a small unlock. Not every sharp edge is a shock. Some are cold fronts. They are contact boundaries where cooler, denser gas sits beside warmer, thinner gas. The pressure can match across the edge. The temperature changes abruptly. The density changes abruptly. The result is a sharp brightness edge without the same heating signature. One term can be defined briefly. A cold front is a sharp boundary between gases of different temperature. 2 sentences return to imagery. Like a smooth layer of oil beside water, it makes a visible interface without violent mixing. Like a thin fog bank beside clear air, it creates a clear edge at the boundary. One sentence explains why it matters. Cold fronts reveal how gas from substructures survives and moves within the cluster. Another visual anchor follows. Inside the cluster, a crescent-shaped edge wraps around a denser pocket. The pocket looks like a soft lens embedded in haze. Along the lens rim, brightness rises sharply. On the far side, brightness falls more gradually. The edge looks like a clean curve. It is not a circle. It is an arc that hints at motion through a thicker medium. The physical detail is the sharp rim and the gentler trailing side. Another payoff arrives as a clear answer. Fronts and shocks are the cluster's way of converting direction into temperature and layering. Infall is guided by filaments. When infall meets the cluster atmosphere, it cannot remain a simple stream. It becomes a boundary. That boundary carries information about speed, direction, and density. The boundary also moves. Over time, it drifts outward or dissolves. It can fade into the general atmosphere. The everyday analogy becomes the main comparison for this section. Like a slow crease travelling through a thick quilt, a shock carries a change across a wide surface while staying narrow. The quilt does not tear. It compresses locally. The crease travels. Behind it, the quilt is slightly warmer and denser. The analogy unlocks a detail. A travelling crease can remain visible longer where the quilt is smoother. In a cluster, a front can persist where turbulence is weaker. A scale shift arrives softly. A quilt crease can move across a bed in seconds if pushed. A cluster front can move across millions of light years over hundreds of millions of years. The same idea persists. The pace changes. Another visual anchor arrives at the right interval. Far from the core, a faint arc sits near the cluster's outer halo. The arc is broad and dim. Its edge is still sharper than the surroundings. It traces a gentle curve that wraps partway around the cluster. It looks like a distant shoreline inside the halo. The physical detail is the outer rim and the interior brightening. Another payoff arrives as a quiet mechanism. Outer shocks can mark where fresh infall meets the cluster for the first time. They can also mark the passage of past mergers. Each event leaves an expanding shell of altered gas. The shell is not always complete. It can be broken where the medium is uneven. It can be brighter where gas is denser. It can be faint where the outskirts are thin. The limit of observation enters with calm precision. Shocks and fronts are identified through brightness and temperature structure. Brightness depends strongly on gas density. Thin edges can be exaggerated. Temperature is harder to infer. It relies on spectral shape and sufficient signal. In the outskirts, the signal can be weak. Background contamination can blur the edge. Projection adds confusion. Two unrelated layers along the line of sight can mimic a single sharp boundary. Resolution adds another limit. A thin front can be smeared into a wider gradient and lose its identity. Models can separate shock and cold front, yet different assumptions about geometry change the inferred strength. The existence of boundaries remains clear. Their precise properties can vary. A final visual anchor steadies the tone. A cold front curves like a smooth blade through the cluster haze. On one side, the gas is denser and cooler. On the other, it is thinner and warmer. The edge stays crisp for a long time. It slowly frays at its ends. It slowly dissolves into the background. The section closes with a gentle step forward. Filaments continue feeding these basins through narrow lanes. The next section follows those lanes and the steady inflows that connect the web strands to the cluster's growing core. A filament can feel like a quiet bridge, yet it acts as a steady conveyor between emptiness and density. Filaments feed clusters through long inflows that narrow into layered entry regions, where gas and dark matter join the basin. In that region, the filament is thick and dim. It carries a spine of higher density. It carries a sheath that fades outward. The cluster sits ahead as a broader haze with a rounded core. Between them, a transition zone forms. The first payoff arrives early. Feeding is not a one-time event. It is a continuous drift that adds mass in small repeated increments. Each increment is too subtle to notice alone. Together they build the core over billions of years. A slow, visual anchor opens. A long ribbon of faint haze stretches across darkness. It bends toward a bright knot. As the ribbon nears the knot, it becomes slightly thicker. Its edges become less distinct. The ribbon's sheath blends into the cluster's outer atmosphere. At the blending zone, a thin band appears. It is brighter than the surrounding haze. The band curves around the entry point like a soft collar. The physical detail is the collar's sharpness compared with the filament's diffuse body. It marks where directed flow becomes mixed motion. Another payoff arrives as a clear mechanism. Infall along a filament is partly along axis and partly inward. The along axis drift delivers material to the junction. The inward drift pulls material toward the spine. Near the cluster, the basin adds a stronger inward pull. The flow accelerates. It then slows and spreads as it meets denser gas. That slowing turns motion into heat and turbulence. The band forms because compression is focused into a thin layer. One term can be used and kept simple. An accretion flow is matter moving inward under gravity. Two sentences return to plain imagery. Like a stream entering a lake, it narrows in the channel and then spreads at the shore. Like mist sliding into a valley, it thickens where the slope deepens and thins where the slope relaxes. One sentence explains why it matters. Accretion flows set how fast clusters grow and how their outer layers form. The main number arrives calmly. A filament can deliver material for billions of years like a drip that slowly fills a basin until the waterline rises. The comparison is about persistence. A slow supply can matter more than a brief surge. This duration also explains the layered edges seen at cluster outskirts. Repeated arrivals create repeated boundaries. Another visual anchor appears at the right pace. Along the filament, small knots ride within the spine. As they approach the cluster, their surrounding haze is stripped and stretched. A faint tail trails behind each knot. The tail is a gradient that fades outward. The front edge is sharper. The back edge is softer. The physical detail is the asymmetric wake. It shows that the cluster atmosphere resists motion. It also shows that feeding is not smooth. It has texture and interruptions. Another payoff resolves a quiet question. Filament feeding can be cooler than the cluster atmosphere at first. Cooler material can slide in as a narrow lane. It can remain coherent for a time. It forms a contrast in temperature and density. The contrast can create a boundary that looks like a front. Over time, mixing warms and spreads the lane. The lane becomes part of the general atmosphere. The transition is slow. It is guided by gradients rather than collisions. The everyday analogy becomes the main comparison for this section. Like a long band of sediment carried by a slow river into a still reservoir, a filament brings material that settles into layers near the entry. The reservoir does not swallow the river instantly. A delta-like region forms. Channels spread and fade. Edges sharpen where flow is focused. The analogy unlocks a detail. The first deposit is not the deepest. It is the most recently delivered. In a cluster, the outer layers often contain the freshest infall. The inner regions contain older mixed material. The scale shift arrives softly. A river can build a delta over years. A filament builds a cluster boundary over hundreds of millions of years. The logic stays gentle. The clock expands. Another visual anchor arrives. The filament approaches the cluster from the side. The cluster halo looks slightly brighter along that side. A faint plume extends outward along the filament direction. On the opposite side, the halo looks rounder and calmer. The physical detail is the directional extension. It shows anisotropy. Feeding is not equal from all directions. The web supplies along preferred corridors. Another payoff arrives as a clear takeaway. The cluster grows in a biased way because the web is biased. Filaments define the main lanes. Junctions define the main sinks. Voids define the main sources of relative outflow. The web's geometry controls the growth pattern. That control remains even when local turbulence stirs the gas. The limit of observation enters with calm precision. Feeding lanes are difficult to map because their brightness can be low. Thin inflows can be confused with projection of unrelated gas along the line of sight. Temperature contrasts can be subtle and can be smeared by limited resolution. Mass maps inferred from light bending can reveal the dark scaffold, yet the signal can be noisy in the outskirts. Models help by combining many faint hints. Different model choices can shift the inferred width of lanes and the inferred rate of feeding. The main picture remains stable. Filaments act as persistent conveyors into clusters. Fine details of lane temperature and density can vary with method. Another visual anchor slows the closing movement. At the entry collar, the filament spine dissolves into the cluster atmosphere. The collar curves around the junction like a soft crescent. Inside it, the haze is smoother. Outside it, the haze shows streaks aligned with the filament. The physical detail is the change in texture across the collar. It marks the checkpoint between streaming and mixing. The final payoff arrives as a gentle consolidation. Cluster boundaries are not static shells. They are moving records of feeding. Each layer is a memory of direction and timing. The section closes with a soft step forward. When light passes near these dense junctions, it bends in ways that reveal the hidden scaffold. The next section moves from gas edges to the bending of light and the quiet map it draws. A distant field of light can bend into quiet curves that reveal mass without showing it directly. Gravitational lensing maps the cosmic web because mass gently warps space and changes how background shapes appear. In that region, no beam is drawn as a straight line for long. Light behaves as if the path is nudged by every gradient it passes. The first payoff arrives early. Lensing is not a spotlight. It is a subtle distortion that accumulates along the journey. A dense knot can stretch background shapes into arcs. A long filament can shear shapes in one preferred direction. A void can make the same field look slightly less distorted. The web becomes visible as a pattern of tiny changes. A slow visual anchor opens. A black expanse holds a scattered field of faint galaxies. Their shapes are mostly small ovals. Near a massive knot, several ovals become longer. Their long axes point in a similar orientation. Some appear as gentle crescents. The crescents curve around an unseen center. The physical detail is curvature. It is also alignment. The alignment is a quiet signature of shear. The crescents are not painted on the sky. They are ordinary distant objects whose apparent shapes have been stretched. Another payoff arrives as a clear mechanism. A mass concentration changes the gradient of gravitational potential. That gradient changes the mapping between the source shape and the observed shape. One term can be defined briefly. Shear is a stretching distortion that makes shapes more elliptical. Two sentences return to plain imagery. Like reflections seen through uneven glass straight lines become slightly curved. Like a pattern under shallow water tiles seems stretched along a preferred direction. One sentence explains why it matters. Shear traces the mass distribution even when the mass itself emits no light. The main number arrives gently. A strong lens can produce arcs that span tens of arc seconds like a curve that covers the width of a small coin held at arm's length. The comparison is about apparent size. It keeps the scale human without introducing people. The arcs are small on the sky. Their meaning is huge. They signal a deep basin of mass. Another visual anchor appears at the right pace. Along a filament between two knots, the background ovals show a faint pattern. They are not curved into crescents. Instead, they are subtly aligned. Their major axes lean in the same direction. The alignment changes slowly along the filament. It rotates as the filament bends. The physical detail is the gradual twist of orientation. The twist traces the filament's curvature. Another payoff arrives as a quiet answer. Filaments can be detected even when they are dim in ordinary light. Their mass adds a small but coherent shear. The effect is weak for a single background object. It becomes clear when many objects are averaged. The web is mapped statistically. It is a pattern in a sea of noise. The everyday analogy becomes the main comparison for this section. Like a faint fingerprint on frosted glass, the web appears as directional smear that becomes visible only when the view is angled just right. The smear is not a separate object. It is a change in texture. The analogy unlocks a detail. The fingerprint is clearest where ridges are closest. In the web, shear is strongest near knots and along denser strands. In voids, the imprint is weaker. The scale shift arrives softly. A fingerprint ridge is seen on millimeter scales. A filament ridge is traced across millions of light years. The same idea persists. A gradient leaves a pattern in what passes through it. Another visual anchor arrives. A circular pattern appears around a dense knot. It is not a perfect circle, it is a partial ring. Several arcs lie at similar radii. Between them, the background is less distorted. The physical detail is a ring-like structure made from separate pieces. It hints at a special geometry where many paths are bent similarly. Another payoff arrives as a gentle clarification. Rings and arcs require alignment in distance and geometry. If the background source is in the wrong place, no arc appears. If the lens is less concentrated, only mild shear appears. Absence of an arc does not mean absence of mass. It can mean the alignment is not favourable. That is why weak lensing is important. It uses small distortions across wide areas. It does not rely on rare, perfect alignments. The limit of observation enters with calm precision. Lensing is inferred from shapes that have their own intrinsic variety. A background object can be naturally elliptical. It can be naturally aligned by chance. Noise and shape measurement adds uncertainty. Resolution and blurring can round shapes and hide small shear. The atmosphere of intervening gas does not distort light much, yet unrelated foreground objects can contaminate the field. Projection adds another limit. Mass along the line of sight accumulates. A filament in front of a knot can add shear. A void behind can reduce it. The map becomes a sum of layers. Models can separate layers statistically, yet any single region retains ambiguity. Another limit appears in the source distances. If distances are uncertain, the inferred mass scale shifts. The pattern remains. The calibration changes. Another visual anchor slows the pace. A wide patch of sky shows a gentle swirl in alignment. The swirl traces a large-scale mass pattern. It is not a spiral galaxy. It is an alignment field. The swirl connects two denser regions. Between them, the shear is weaker but coherent. The physical detail is continuity. The alignment does not jump. It flows smoothly across the region like a soft current. Another payoff arrives as a quiet conclusion. Lensing turns the invisible scaffold into a measurable texture. It can reveal filaments that do not glow. It can weigh knots where brightness misleads. It also shows voids as regions with weaker distortion. The cosmic web becomes a map of gradients written into light paths. The section closes with a gentle step forward. Lensing reveals structure at a moment in time. Over time, mergers reshape the web and thicken some strands. The next section follows that slow reshaping and the way the web records its history in growth and layering. A web that seems frozen at one moment is actually a slow river of mergers and rearrangements. The cosmic web evolves because small structures merge into larger ones while filaments thicken and voids broaden. In that region, a filament is not a single strand. It is a bundle of streams. Some streams carry compact knots, some carry diffuse haze. Where streams converge, a node grows. Where streams are diverted, a void becomes cleaner. The first payoff arrives early. Growth is hierarchical. Small halos form first. Larger halos form later by collecting and merging smaller ones. This simple ordering explains why the web looks layered. It also explains why outskirts remember more than cores. A slow visual anchor opens. Two dim knots drift along the same filament toward a larger junction. Each knot has a faint halo. The halos overlap before the centers do. In the overlap zone, the haze becomes thicker. The boundary between the halos is not sharp. It is a gradient that brightens slowly as the distance shrinks. The physical detail is the bridge of diffuse material that forms between them. The bridge looks like a soft band connecting two rounded clouds. Another payoff arrives as a clear mechanism. Mergers begin as overlapping outskirts. The core-to-core encounter is only the final step. Long before that gravity reshapes the surrounding potential, streams are rerouted. Filament directions can bend slightly toward the growing mass. The web adjusts its lanes as the sinks deepen. One term can be defined briefly. A merger is the joining of two bound structures into one. Two sentences return to plain imagery, like two soap bubbles that touch and slowly share a boundary. Their skins deform before they combine. Like two patches of fog drifting together, their edges blend long before the centers align. One sentence explains why it matters. Mergers drive rapid growth at nodes and thicken the connected filaments. The main number arrives gently. A major merger can unfold over about a few billion years, like two slow tides meeting over many cycles until a new shoreline is set. The comparison is about long reshaping. The process is extended. It leaves persistent signatures. Those signatures are not only in the node, they appear along the filaments that feed it. Another visual anchor arrives at the right pace. Near a junction, a filament shows a kink. The kink is subtle. The filament spine curves as if pulled sideways. On the inside of the curve, the spine is thicker. On the outside, it is thinner. The sheath shows a sharper gradient on the inside. The physical detail is asymmetry across the filament. It reveals a nearby mass concentration tugging on the flow. Another payoff arrives as a small unlock. Filament thickening can happen without adding new filaments. It happens when existing lanes capture more streams. As a node grows, it pulls material from a wider region. Streams that once fed a neighboring node can be diverted. The web is competitive. Basins overlap. Matter chooses the deepest descent over time. The result is a slow rebalancing. Some junctions become dominant. Others stagnate. A new visual anchor settles in. A wide sheet between filaments becomes fainter at its center. Its edges grow brighter where they connect to seams. The sheet looks like a thinning veil that is being pinched into lines. The pinching is not uniform. One edge brightens faster, another edge fades. The physical detail is the changing contrast across the sheet. It is a quiet record of redistribution. Another payoff arrives with calm clarity. Voids are not passive. As nodes grow void, interiors lose material more efficiently. The void boundary sharpens. The void becomes larger in relative terms. This does not mean the void pushes outward with force. It means the surrounding walls gain mass and the interior falls behind. Expansion stretches the interior more. The difference increases. The web's contrast deepens. The everyday analogy becomes the main comparison for this section. Like a slow knot forming in a woven net under steady tension, nodes tighten while the open spaces widen. The net is not cut. The threads do not vanish. Tension redistributes them into tighter intersections and broader openings. The analogy unlocks a detail. A knot in a net draws nearby strands inward. Strands straighten and thicken near the knot. In the cosmic web, filaments align and thicken near growing nodes. The scale shift arrives softly. A knot can tighten in minutes in a simple net. A cosmic knot tightens over billions of years. The tendency is the same. The timescale is immense. Another visual anchor appears at the right interval. A cluster halo shows faint shells in its outskirts. The shells are incomplete arcs. They're layered bands where fresh material has joined. One arc is brighter on the side, facing an incoming filament. Another arc is fainter and broken where the outskirts are thin. The physical detail is layering and breakage. The bands are not symmetric. They carry directional memory of past arrivals. Another payoff arrives as a gentle takeaway. The web records time in geometry. Straight, calm filaments suggest long, steady feeding. Bent, kinked filaments suggest recent changes in the sink landscape. Broken shells suggest recent mergers. Smooth profiles suggest older mixing. No single feature is a perfect clock, yet together they point to a history. The limit of observation enters with calm precision. Many of these signatures are faint and extended. Projection can overlap unrelated structures and imitate a merger bridge. Resolution can blur thin shells into smooth gradients. Tracers can bias perception. Bright objects highlight dense regions and hide diffuse bridges. Lensing can reveal mass bridges, yet the signal can be noisy and smeared along the line of sight. Models can reconstruct history statistically, yet different initial conditions can lead to similar present structures. The past cannot be read uniquely from one snapshot. Another visual anchor slows the closing movement. Two halos now share a single larger envelope. The bridge has thickened. The combined outline looks more oval than round. A faint wake extends behind along the filament direction. The physical detail is elongation and a trailing gradient. It marks an ongoing merger not yet fully mixed. The final payoff arrives as a quiet consolidation. Growth by merging is the web's engine. It thickens nodes and reshapes lanes. It sharpens voids by contrast. The section closes with a gentle step forward. As the web evolves, the influence of unseen components remains central. The next section moves into how different dark matter behavior would change the web's texture and the softness of its smallest strands. A tiny change in dark matter behavior would rewrite the web's finest threads without changing the grand outline. The cosmic web's texture depends on how easily dark matter clumps on small scales and how smoothly it streams before it can settle. In that region, the large filaments and voids remain. The difference appears in the thinness of strands and the graininess of knots. The first payoff arrives early. Dark matter is not seen, yet its microscopic properties set the smallest structures that can form. If small clumps are suppressed, the web becomes smoother. If small clumps are abundant, the web becomes more granulated. One term can be defined briefly. Free streaming is the smoothing motion of particles that erases small clumps. Two sentences return to plain imagery. Like fine dust that stays suspended and blurs sharp edges free, streaming smooths the smallest wrinkles. Like warm butter that softens tiny ridges compared with cold butter, it rounds the finest texture. One sentence explains why it matters. The smallest web features carry clues about what dark matter can do. A slow visual anchor opens. A filament stretches across darkness toward a node. Along its spine, faint beads appear. In one case, the beads are numerous. They sit close together like a string of small pearls. In another case, the spine is smoother. Only a few larger beads appear spaced farther apart. The physical detail is bead spacing and spine thickness. The contrast is not in the filament's existence. It is in its grain. Another payoff arrives as a clear mechanism. Small halos form from small initial fluctuations. If dark matter smooths those fluctuations early, fewer small halos appear. The first structures then grow from larger seeds. Filaments still form. Nodes still grow. The difference is in substructure. The outskirts of clusters would have fewer small companions. The void interiors would be even emptier of tiny knots. The web would look cleaner between major junctions. The main number arrives gently. A suppression scale could correspond to masses around those of small dwarf galaxies, like removing the smallest pebbles from a beach while leaving the larger stones. The comparison is about missing small pieces rather than exact masses. The absence changes the texture underfoot. In the web, the absence changes how many small knots populate filaments. Another visual anchor arrives at the right pace. Near a cluster edge, faint tails trail behind incoming small halos. In a grainy web, many tiny tails overlap and create a mottled texture. In a smoother web, the same region looks more uniform. The haze is present, yet it lacks speckling. The physical detail is mottling versus smooth gradient. Another payoff arrives as a small unlock. The web's large-scale pattern is set by gravity acting on broad fluctuations. Many dark matter models match that large pattern. The discriminating information hides in small scales and in how quickly small structures appear. That means the test is subtle. It lives in statistics of weak lensing. It lives in counts of small halos. It lives in the thickness and continuity of faint filaments. A new term can appear and stay short. Substructure means smaller halos inside larger halos. Two sentences return to plain imagery. Like knots within a rope, substructure adds stiffness and unevenness. Like bubbles trapped in ice, it adds small bright and dim spots. One sentence explains why it matters. Substructure changes how a matter accretes and how lensing distortions vary across a cluster. The everyday analogy becomes the main comparison for this section. Like a sheet of paper made from coarse pulp versus fine pulp, the web can be rough or smooth while keeping the same overall shape. The coarse sheet has visible fibers. The fine sheet looks continuous. The analogy unlocks a detail. Fibers guide how tears propagate. In the web, small knots guide how streams split and merge. When fibers are absent, patterns are simpler and less branched at small scales. The scale shift arrives softly. Fiber thickness is measured in fractions of a millimeter. Filament texture is measured across thousands of light years. The same idea persists. Small-scale texture influences larger patterns of flow. Another visual anchor appears. A void boundary is traced by a thin sheet. In a grainy web, the sheet is punctured by many small knots. They pepper the wall like tiny dim bulges. In a smoother web, the sheet looks cleaner. It bends gently without many bumps. The physical detail is bumpiness along a boundary layer. Another payoff arrives with calm clarity. Bumpiness matters because it seeds later growth. Each bump can collect more mass. Each bump can become a new branch. If bumps are missing, the web remains simpler, longer. Nodes still dominate, yet the number of small branches decreases. This changes the distribution of matter around filaments. It also changes how rapidly filaments thicken at their edges. The limit of observation enters with calm precision. The smallest web features are faint and hard to measure. Weak lensing averages over many background shapes. Noise can hide small variations in shear. Projection can place unrelated clumps along the same sightline and imitate extra substructure. Resolution can smear small halos into a smooth background. Tracer bias adds another limit. Bright objects prefer dense regions and can miss tiny halos in low-density environments. Simulations can predict differences, yet they depend on assumptions about gas behavior and feedback-like processes, even without human elements. Disentangling dark matter texture from ordinary matter effects remains challenging. The large pattern is easier. The fine texture is where uncertainty lives. Another visual anchor slows the closing movement. A filament spine fades into a node. Along the spine, the bead pattern gradually changes. Small beads become fewer near the node as they merge into larger concentrations. The physical detail is the changing bead size and spacing. It shows a continuum from fine to coarse structure. The final payoff arrives as a gentle consolidation. Dark matter behavior sets the smallest seeds. Gravity amplifies what exists. The web's grand architecture is robust, yet its fine grain holds clues. The section closes with a soft step forward. Beyond texture, the web also shapes how environments differ across space. The next section widens to those consequences and follows how voids and nodes create distinct conditions over cosmic time. A void looks like absence, yet it is an active part of the web's design. Voids' walls and nodes create distinct environments because gravity pulls matter into strands and leaves broad interiors comparatively rarefied and smooth. In that region, the difference is not a boundary drawn with ink. It is a gradient of density and temperature that changes how gas drifts and how structures continue to grow. The first payoff arrives early. The web is not only a map of where matter gathers, it is also a map of where matter does not gather, and that absence shapes everything around it. A slow visual anchor opens. A vast, dim basin stretches across space. Its interior haze is thin and uniform. Near its edge, the haze thickens into a pale wall. The wall is not flat. It is corrugated. It has gentle ridges that run parallel for long distances. At the ridges, faint filaments branch like seams. The physical detail is the steepening gradient at the wall. It is a soft cliff in density rather than a sharp line. Another payoff arrives as a clear contrast. Inside a void, gravity's pull is weaker in its interior because nearby mass is sparse. That does not mean gravity is gone. It means the net pull is shaped by distant walls. Material in the interior drifts slowly toward the boundaries. Over time, the interior becomes cleaner. The boundaries become denser. A single number arrives calmly. A mature void interior can hold about 1/5 of the average matter density, like a fog that has thinned until only one wisp remains for every 5 in a denser region. The comparison stays gentle. It translates a ratio into a texture. A second visual anchor appears. At the void wall, a thin sheet of gas glows slightly brighter than the interior. The sheet has layers. One layer is thicker where a filament meets the wall. Another layer is thinner and more translucent farther away. The edge of the sheet is marked by a faint rim. The rim curves and then fades. The physical detail is layering within a boundary surface. The layers are not static. They drift and fold as streams join from different directions. Another payoff arrives as a small unlock. The wall is a collector. It gathers slow inward drift from the void interior and faster inflow along filaments. The meeting of slow and fast creates shear. Shear creates mixing. Mixing smooths some features while sharpening others into thin edges. One term can be used and kept short. Entropy is a measure of heat spread and compression history. The definition stays brief. 2 sentences return to imagery. Like warm air spreading through a cavern, heat fills available space and softens sharp contrasts. Like a thin layer of oil sliding over water interfaces can stay crisp, while the interior remains calm. One sentence explains why it matters. Entropy helps determine whether gas stays as a coherent layer or blends into a wider atmosphere. A scale shift arrives softly. A thin boundary layer can be narrower than a single galaxy. The wall itself can extend for hundreds of millions of light years. The same physics of gradients applies across both scales. The void interior remains slow. The wall remains busy. Another visual anchor arrives at the right pace. Along the wall, a filament appears as a brighter seam. The seam has a spine that is slightly thicker near a node. It tapers as it runs away. Small knots pepper the spine. Each knot has a faint tail that points along the filament direction. The physical detail is taper and trailing gradient. The seam is not centered in the wall. It sits on the denser side, showing that the wall itself has an inner and outer face. Another payoff arrives with calm clarity. Environments differ not only in density but also in the pace of change. In dense nodes, orbits and infall reshuffle matter frequently. In void interiors, reshuffling is slow. A feature in a void can persist longer because fewer streams cross it. A feature near a node can vanish quickly into mixing. This difference is a quiet clock. It helps explain why some regions look smoother and others look layered. The main analogy becomes the steady comparison for this section. Like a stretched soap film that thins in the middle and thickens at the frame, the cosmic web thins inside voids and thickens at walls and seams. The film does not tear everywhere at once. It forms ridges where tension gathers. It forms smoother regions where tension is spread. The analogy unlocks a detail. A ridge on a film can guide where the next ridge forms. In the web, a wall can guide where filaments persist and where new branches appear. Another visual anchor follows. A node sits at the intersection of several seams. Around it, the wall's sheet folds into a rounded basin. The basin shows a brighter, ring-like boundary where gas is compressed. Inside that boundary, the glow is smoother. Outside it, the wall is mottled with faint ripples. The physical detail is a ring-like compression feature that is incomplete. It is brighter on the side facing a strong filament. It is fainter on the side facing the void. Another payoff arrives as a gentle answer. The void is not empty, yet it is an environment where growth is delayed. Small fluctuations that might become knots in a filament can be stretched and diluted in the void interior. Gas there can stay more diffuse. It can cool slowly. It can remain harder to detect. Meanwhile, the walls receive more material and become denser. The difference grows with time. This is a feedback without drama. Density draws more inflow. Sparse regions receive less. Another scale shift arrives. Over a few million years, a local ripple changes little. Over billions of years, the void interior becomes noticeably cleaner and the walls noticeably sharper. The web's contrast is built through patience. The limit of observation enters with calm precision. Void interiors are faint in most tracers. Emission depends strongly on density, so thin gas can fall below detection. Weak lensing signals are also weak where mass is low. The distortion field can be dominated by structures in front of and behind the void. Projection can imitate a wall where none exists in the target region. Resolution can blur a thin sheet into a broad gradient and hide layering. Models can infer void profiles statistically, yet the inferred depth depends on how distances and selection are handled. The void remains real. Its exact smoothness and exact density contrast can vary with method. Another visual anchor slows the pace again. Deep inside the void, the haze is nearly uniform. It shows only a very faint gradient toward the wall. The gradient is so gentle that it is easy to confuse with noise. At the wall, the change becomes obvious. The sheet looks like a pale curtain. Its edge is scalloped. The scallops are wide. Their crests point toward nearby seams. The physical detail is scalloping on a boundary surface. Another payoff arrives as a quiet consolidation. The web is a set of environments stitched together. Filaments deliver, walls collect, nodes mix and heat. Voids preserve smoothness and delay growth. Each role supports the next. Without voids, there would be less contrast. Without walls, there would be fewer seams. Without seams, nodes would grow more slowly and more symmetrically. The section closes with a gentle step forward. The web's environments change gradually as expansion stretches space and gravity gathers matter. The next section widens further into the long timeline, and the calm way the web moves from early texture to mature structure. The web's shape is a memory, and the memory is written by a steady contest between expansion and collapse. The cosmic web matures as gravity gathers matter into nodes and filaments, while expansion stretches distances and slows new growth. In that region, the result is not a sudden stop. It is a gradual easing. The web keeps changing, yet the changes become more subtle with time. The first payoff arrives early. Expansion does not erase the web. It changes the rate at which new structure can form. Early on, small differences grow quickly. Later, the same differences grow more slowly. This is why the web looks increasingly settled at late times. A slow visual anchor opens. A wide lattice of filaments spans a vast volume. The filaments are thick near nodes. Between nodes, they taper into faint spines. Voids between them look smoother than before. Their walls look more continuous. The physical detail is sharpening at walls and thickening at knots while interiors stay dim. Another payoff arrives as a clear mechanism. Growth depends on how easily matter can fall into potential wells. When expansion dominates the background, density drops and infall becomes less efficient. Streams still flow along filaments, yet the supply rate decreases. Nodes still merge, yet major mergers become rarer. The web evolves by rearrangement rather than constant new branching. One term can be defined briefly. Growth factor is the measure of how density contrasts increase over time. Two sentences return to imagery. Like a ripple that rises quickly in a shallow pond, early growth amplifies small waves. Like a ripple in a deep lake, later growth spreads and softens instead of rising sharply. One sentence explains why it matters. The growth history shapes how thick filaments become and how empty voids appear. The main number arrives gently. The age of the universe is about 14 billion years, like a library of seasons so long that each chapter is measured in billions of years. The comparison keeps time as a calm stack of intervals. It sets the scale for the next steps. Over that long span, early chapters are busy. Later chapters are quieter. Another visual anchor appears. A filament cross-section shows a layered profile. The core is denser. Around it sits a broader sheath. The sheath fades gradually into the surrounding void. The boundary is not a line. It is a gradient that becomes shallower with time as the outskirts relax. The physical detail is the changing steepness of the gradient. The gradient is steeper near nodes. It is gentler far away. Another payoff arrives as a small unlock. The web's late-time change is often about smoothing within existing structures. Streams settle into stable corridors. Some side branches fade as supply weakens. The most persistent filaments remain connected between major nodes. The web becomes less tangled. It becomes more skeletal. This does not require removing matter. It requires shifting where matter spends time. A visual anchor arrives at the right pace. A node shows a faint envelope that extends outward in an oval shape. The oval is aligned with its main filament. Along the long axis, the envelope is slightly brighter. Along the short axis, it fades more quickly. The physical detail is elongation and directional fall-off. This elongation is a fossil of anisotropic feeding. It records where streams arrive most often. Another payoff arrives with calm clarity. The web's geometry is not random. It has preferred directions set by the larger scale fluctuations. Those directions persist. Even as individual knots merge and relax, the larger alignment remains. Filaments tend to lie along those directions. Walls tend to span between them. Voids tend to expand in the gaps. The large pattern is a slow blueprint that the smaller pattern fills in. The everyday analogy becomes the main comparison for this section. Like a slowly drying river delta, channels persist but carry less fresh water over time. The delta still has its main branches. Small side channels silt up. The overall shape remains recognizable. The analogy unlocks a detail. In a delta, banks become more defined as flow settles into fewer paths. In the web, filaments become more defined relative to voids as the interior thins and the corridors remain. Another scale shift arrives softly. A delta can change over years. The web changes over billions of years. The same sense of settling applies. The late-time web is a calmer version of the early-time web. Another visual anchor appears. A void wall shows a scalloped edge, yet the scallops are broader than before. Small ripples have faded. Larger undulations remain. The physical detail is the loss of fine corrugations while large curvature stays. This is a signature of reduced small-scale growth. Fine structure stops multiplying. Coarse structure persists. Another payoff arrives as a gentle answer. The web becomes a record of when growth slows. If growth stays efficient longer, fine structure remains stronger. If growth slows earlier, the web looks smoother. These differences can be tested by comparing the statistical texture of lensing maps across time. The test is subtle. It requires measuring faint shear patterns and their change. It also requires understanding how traces relate to mass. The limit of observation enters with calm precision. Measuring growth over time demands comparing structures at different distances, which means comparing different cosmic epochs. Distance estimates can be uncertain. Selection effects can bias which regions are sampled. Projection can mix structures along the line of sight. Lensing noise can obscure small changes in shear amplitude. Simulations can match many observables with different parameter combinations. Degeneracies remain. The growth history is constrained yet not uniquely pinned by any single measurement. Another visual anchor slows the pace again. A long filament between two nodes shows a gentle thinning in its midspan. The midspan has a lower density core than the ends. It looks like a rope that is thick near anchor points and slimmer between them. The physical detail is the necking along the filament's length. The necking indicates that matter is still draining toward the nodes. The process continues even late. It is slow. It is persistent. Another payoff arrives as a quiet consolidation. The mature web is shaped by early conditions and late-time pacing. Expansion stretches space and reduces the background density. Gravity continues to gather along existing corridors. The result is a web that changes by refinement. Walls become cleaner, voids become emptier, nodes become more massive and more relaxed. The section closes with a gentle step forward. After the long timeline, the final section settles into a soft, wide view. It gathers the arc into a calm ending without suspense, and lets the web fade into a steady, restful geometry. The cosmic web does not need a finish line to feel complete. Its calm resolution comes from stability. Gravity keeps shaping matter into filaments and nodes. Expansion keeps stretching the space between them. The web persists as a quiet balance. The first payoff arrives early. A web can keep evolving while also becoming restful. The large pattern remains. The fine details change slowly. A slow, visual anchor opens. A wide volume holds faint threads. The threads curve gently across dark gaps. Where several threads meet a node appears as a soft swelling. The swelling has a bright rim of compressed gas. The rim is not uniform. It is thicker on the side, fed by the thickest filament. The physical detail is a ring-like edge with a clear gradient. The glow fades into a halo. Beyond the halo, the filament sheath thins into near invisibility. Another payoff arrives as a simple anchor. The web is a geometry of gradients. Dense regions are not only denser, they are also places where gradients are steeper. Steeper gradients guide flows more strongly. Gentle gradients guide flows slowly. This is why void interiors remain smooth. This is why walls and filaments remain persistent corridors. A visual anchor arrives at the right pace. A filament is seen in cross-section as a pale cylinder. Its core is slightly brighter. Around it sits a wider coat of diffuse gas. The coat shows faint layering. The layers shift from smooth to mottled near a branching point. The physical detail is the change in texture along a boundary layer. The branch leaves behind a tapered wake. The wake is a thin wedge of slightly higher density. It points away from the node. Another payoff arrives as a small unlock. The web's shape is a memory of initial conditions and later pacing. Early on, small differences grow fast. Later differences grow slower. The web's backbone forms early and remains. Late time brings refinement. Refinement means less new branching. It means smoothing within corridors. It means continued drainage toward nodes. A scale shift arrives softly. The layering around a filament can change over a span smaller than a galaxy. The alignment of filaments can persist across hundreds of millions of light years. The same gravity shapes both. It simply acts at different rates. The analogy for this final section becomes steady and gentle. Like a sheet of fog cooling over a plane, the web's contrast sharpens at edges as the interior thins. The fog does not vanish everywhere at once. It becomes clearer in the center. It gathers along low ridges. The analogy unlocks a detail. Cooling makes the fog's boundary easier to see. In the web, slow settling makes walls and filaments easier to distinguish from voids. Another visual anchor arrives. A void interior looks like a dim basin. Near its center, the haze is nearly uniform. Toward the wall, the haze shows a faint slope. The wall appears as a pale curtain. The curtain is scalloped. Each scallop is wide and shallow. Along the scallop crests, thin seams run like stitching. The physical detail is scalloping and seam-like ridges. The seams converge toward a node. At the node, the curtain folds into a rounded bowl. The bowl shows a brighter arc on one side. The arc marks compression, where inflow meets an existing layer. Another payoff arrives as a calm answer. Voids and nodes are not opposites. They are complementary. Voids provide the empty volume that makes the web visible as a contrast. Nodes provide the anchors that keep corridors aligned. Walls connect them as surfaces. Filaments connect them as lines. Each element gains meaning from the others. Another scale shift arrives. Over 1 billion years, like the time it takes a continent to drift the width of a sea, the web's refinements become noticeable. A filament can become slightly more defined. A void can become slightly cleaner. A node can become slightly more relaxed. Over shorter spans, the same changes are subtle. The main number stays quiet and safe. It marks the slow tempo. A visual anchor arrives at the right pace. In a node, the gas shows a smooth central glow. Around it, a faint shell appears. The shell is incomplete. It is thicker where the main filament meets the node. It is thinner on the void-facing side. The physical detail is an asymmetric shell and a clear gradient. The shell's inner edge is sharper than its outer edge. This shows compression at the boundary and diffusion beyond it. Another payoff arrives as a final mechanism. Even late, the web continues to channel matter. The channels remain because gravity still points toward gradients. The channels weaken because the background becomes thinner and expansion stretches distances. The result is a web that keeps its form while slowing its tempo. This is why the late universe feels quieter in structure growth. The limit of observation enters with calm precision. Dark matter does not emit light. Its distribution is inferred indirectly. Lensing maps depend on subtle distortions of background light. Those distortions are small and noisy. Gas emission depends strongly on density and temperature. Thin regions can fall below detection. Projection along the line of sight can mix walls and filaments from different distances. Distance estimates can blur time ordering. Simulations can reproduce a similar web with different parameter combinations. This creates degeneracies. The web is well supported as a framework. Its exact fine texture remains harder to pin down everywhere at once. Another visual anchor slows the pace again. At this distance, the web resembles a faint net suspended in darkness. The net is not uniform. Some strands are thick and continuous. Some strands fade and reappear. The gaps between strands are broad and calm. The node intersections are steady highlights. The physical detail is the fading thickness along strands and the soft halos around nodes. The halos overlap slightly where corridors are close. Where halos overlap, the background appears subtly brighter. Another payoff arrives as a quiet consolidation. The web is the large-scale consequence of simple rules. Matter responds to gravity. Expansion stretches space. Small differences grow into large contrasts. Corridors form because flow prefers the steepest gradients. Voids expand because they are underdense compared with their surroundings. The result is a universe that organizes without sharp boundaries. It organizes through gradients and time. The ending settles gently. The web remains. Its changes continue, yet they slow. The pattern holds enough steadiness to rest within it. The final view stays wide. Threads soften into the dark. Nodes glow quietly at intersections. The scene lingers in a calm geometry and then becomes still.